In our next lesson, I would like to kind of check out something a little bit different. Up to this point, we've been submerging things that are very heavy. So if I think about it, any object that's very heavy, things that are denser than water itself, don't they sink? So when we put them into water, the actual object completely submerges itself. Now the volume of the submerged object, isn't that equal to the amount of water that it pushed out of the way? Now when we start thinking about things like boats, for example, I have a little Sea Ray boat, motor around like that. I don't want to be under the water. I want the boat to actually sit on top of the water. So if we draw a picture of that, if we have the water itself here, part of the boat is actually submerged underneath the water. So if I put the boat in the water, doesn't it push the water out of the way? And that water that gets pushed out of the way creates a buoyancy force. So in the boating situation, I've got my weight of the boat pushing down, and I've got the buoyancy force pushing upward. Well, if you think about it, aren't boats relatively light? I don't make boats out of rocks. You put your rock boat in water, it's going to sink because the rock is so heavy. So they make a boat kind of in the shape of a shell so that the material itself actually displaces a lot of water. So the only part of the boat that's under the water is this part. Now the water that gets pushed out of the way, if we take the weight of that, that's the buoyancy force itself. All right, now let's try a situation here. I've got a block here, maybe it's an ice cube, maybe it's the iceberg that's going to sink the Titanic. Hey, who knows? But this object is lighter than water, and it has a tendency to float out of the water. So part of it's submerged, part of it's underwater. Icebergs themselves are made out of ice. That's why they call it an iceberg. All right? And ice has a little less density than water itself, so they have a tendency to float. So a lot of the iceberg is under the water, but a lot of it just, not so much of it starts to poke out up above. So you got to be careful, especially if you're in a cruise ship going by and you're in the 1930s, you better wear your jacket. All right, now I'm looking at this ice cube. It's partially under the water. So let's draw out the forces here. So if we draw the forces, we know that the ice, this block, let's say it's a block of wood. The block of wood's floating on top of the water. It has weight to it. All right, now, if I look, a certain portion of that is actually under the surface of the water itself. And there's a buoyancy force pushing upward. Now, in the last problem, when I had a rock, didn't I have to tie a string to it and then hold the string so that the rock didn't sink all the way to the bottom? So in this case here, why don't I need a string? Well, if you look at it, the ice cube itself, it floats. I don't need a string. It's happy to do it, and it's going to float. Anytime I put the ice cube or a block of wood in the water, I don't need a string to hold it up. It's going to float on the surface itself. All right, now if we look here, there is no tension from any string or whatever. So we can conclude a few things. All right, what's true about the buoyancy force? The buoyancy force is equal to the weight of the object itself. So if we look here, this mg is the weight of the ice cube or block of wood. I'll call it a wood block. Okay, now the buoyancy force, however, if we look, is created by the water. What water? It's the water that was pushed out of the way by the block. So on this side, when I apply this formula, density is equal to G times V equals mg. This volume is not just any volume. That's the volume of the water pushed out of the way. It's not the volume of the block. Well, if you look about it, isn't a lot of the block in the air? The only part that counts towards the buoyancy force is the part of the block that's actually underneath the water, below the water line itself, being pushed out of the way. So, let's take a look at this equation. This is the density. Who's creating the buoyancy force? The buoyancy force is created by the water displaced by the block. This is the density of water, times 9.8, times the volume of the water. So this is all about the water creating that buoyancy force. On this side, this is the mass of, that's the mass of the block itself, and then times G. So on this side, it's about the block. On this side, it's about the water pushed out of the way by the block. And then these two things have to be equal to each other, Otherwise, excuse me, the block would rise or the block would sink. So if I use my hand and I push it down a little bit, it's going to pop back up again. And it's going to pop up and reach an equilibrium when these two things are actually equal to each other. So knowing this, can we now figure out how high or what percentage of the block itself is out of the water? And we're going to do that in the lab, actually at school. So we're going to look forward to doing this experiment when we get back.